Thank you. Yeah.
All right. Should I start?
Yeah.
All right. Thanks for the invitation. Thanks to everyone who come to my talk today. So last time I presented some large-scale regularity, sometimes called uniform regularity estimate for solutions of elliptic equation with rapidly oscillating and periodic coefficients. And today, my goal is to present another approach to this type of estimate, which has its advantages compared to the one I used last time, the compactness. So let me just first start by recall the problem we try to study here. So we consider a family of elliptic operators in divergence form. So just for the simplicity of presentation, I'm looking at the scalar case, but everything I mentioned today works for elliptic systems and also parabolic systems. So we consider this divergence form operator. The coefficients has a parameter sitting in the denominator of the variable x over epsilon. Epsilon is small. And we are assuming the coefficient matrix without epsilon, the rescale one, is real, bounded, and uniformly elliptic. Some of this result can be extended to complex coefficients. It's not a big deal there, but we are assuming uniform elliptic. We also have a structural condition. Here, the simplest one we have is periodic. So A here is assumed to be one periodic, and that is periodic with respect to the standard integer lattice. If you have an arbitrary lattice, you can always use a linear transformation to change to a integer lattice. So again, this is other conditions. So we have ellipticity, uniform ellipticity, periodicity with respect to lattice, ZD. As I mentioned already, all results hold for systems in divergence form. Okay. So the estimate I showed already using compactness last time is this one. This is an interior Lipschitz estimate. So for simplicity, we're assuming the right-hand side of the equation is 0. And after rescale, you can always just look at a unit ball. So what we want to prove here is that if you have a ball center at 0 of radius r, and r is between epsilon and 1. So the lower bound is referred to the large scale. Anything below epsilon is a small scale estimate. So what we want to show here is that the L2 average of the gradient of the solution over the ball of radius r is controlled by the L2 average of the gradient of the solution over the unit ball. And the constant depend only on the dimension and the ellipticity. In particular, it does not depend on the parameter epsilon. And what's more here, for this large scale estimate, no smoothness condition is required. The coefficient A is just bounded measurable, and of course elliptic and periodic here. Okay, so this is the one we proved using compactness and the homogenization series. So basically, you argue by contradiction, and suppose it's not true, then you take the limit, but the limit is a solution of a homogenized equation, which has constant coefficients. Therefore, the limit has all the regularity you want it, and you want to conclude that the sequence should also have some regularity, and that's the idea here. Proved by compactness. Compactness means it's proved by contradiction here. So today we're going to present a direct approach. This method was first used in this homogenization setting by Charles Smart and Scott Armstrong. So here we're not going to argue by contradiction, rather it's a direct approach. And if you recall, the argument we used last time by compactness, we have to involve the corrector. So there are two steps, actually, So in the first step, you use compactness to gain a small step. In the second step, you iterate the gain you obtain in the first step. But in order to carry out the second iteration, you need the rescaled solution to minus something, minus a linear function, minus another term, which is the corrector, to be a solution of the original equation for different parameters. And that's why the corrector has to be involved. But this direct approach do not involve the corrector of the, so it has a lot of advantage. In particular, it can be applied to non-periodic setting where the estimate, although you do have a corrector, but the estimate of corrector is not good. And it also applied to boundary estimate. Although we have a compactness method for a boundary regularity, but the proof is rather difficult. Lots of machinery has to be used here. So here, the only disadvantage here is that this will require something called a Dini convergence rate. So the first step, in order to carry out this argument, is that you have to prove a convergence rate for the homogenization problem. And this, of course, in different settings can be done. So in particular, when you deal with boundary regularity, it's not a problem. But in some non-periodic setting, it can also be done by some other approach. Okay. So you'll see what are we talking about here? How do we carry out in the interior case? All right. So the first step here is a setup. So remember, how do we prove Lipschitz estimate? So for a function being Lipschitz, you try to measure. You're not going to take the derivative. Once you take a derivative, a lot of things cannot be estimated. So what we want to do is take an approach that when a function has derivative, it means that it's well approximated by a linear function. Okay, so we subtract a linear function. M here is a vector m dot x. And then you minus some constant. So in other words, you try to measure the difference between your solution and the best approximation by a linear function. And then you take the average, and then you properly scale it, because here you subtract a linear function, you have to divide the average by R. So that's the function I call H of R here. Okay, so if you only look at this function, I don't need the function to be a solution. It can be any function. So what I'm saying here is that you can use this infumio to in the place of the L2 average of a gradient here. Okay, so if I recast the large scale Lipschitz estimate, what we want to show here is that this function H of R is bounded by the L2 average of the solution without a gradient. On the scale 1, you can freely change from gradient to non-gradient, one side by Katropoli, the other side by Poincaré. So this is the estimate what we need to do. All right, so how do we do this? Well, here is the key observation. Okay, so what we're going to look at here is that we're going to compare H of R with H of theta R. Theta is a small number. So we compare. So what we want to show here is we expect this H of R is kind of have some decay. So if I compare H of theta R with H of R, the ratio should be small when theta is small. And so that's the idea. So what do we do here in the first step? I simply replace U epsilon by another function W to be chosen. And this is just a triangle inequality. Just you in the place of U epsilon, you replace by W, and the difference is given in the second term. There's nothing else, just a triangle there. In the next step, I'm assuming that this function W is very good, has all the regularities. In particular, let's say W has C1 alpha regularity. Okay, so I expect this. When I measure the difference between W and its best approximation by a linear function, it kind of decay in the right way. So I have, when I go from theta R to R, I decrease. I mean, it's certainly have a 1/2 come out here, because I expect that that H of R to be in the power of R, some sigma there. And I copy the second term, right? So here I'm assuming the W has some regularity. Again, no restrictions otherwise for this function, okay? And then you just going back for the first term, you go back to U epsilon from W. Again, this is just a triangle. So when you do that, you generate another error term. And this two error term can be combined into one. So I'm just change the constant to some constant depending on theta. So it depends on theta, that's fine. Theta, once it fixed, theta will be a constant. So theta will be small to be chosen. W is also supposed to be C1 alpha, and is also to be chosen. And later on, when we choose W, we're going to choose W to be a solution of the homogenized equation for the operator L epsilon. So that's the key observation in this argument. And this is I'm assuming this has been used frequently in the study of linear and nonlinear PDEs. It's a kind of perturbation argument here. Do you have any questions, please? All right. So let's now try to summarize this. What are we trying to do here? So the moral of the story here is that if you have a function which is well approximated at every scale greater than epsilon by a function with C1 alpha estimate, then your function should be Lipschitz at all scale larger than epsilon. Okay, so that's what the previous observations summarize in this way here. Okay, so so again, let's just recall this function h of r, capital H of r. Let's assuming that this m, which is a vector in Rd, is the infield is achieved at some vector. I call it m tilde sub r, and I still keep the q arbitrary there in the infield here. Okay, and I define the absolute value of mr tilde to be little h of r. Okay, so if you put in this together, you'll see that again it's a triangle inequality that oh, I'm sorry. The first inequality is just Kachopoly. So that's a Kachopoly for divergence form equations. The L2 of the gradient is bounded by L2 of the solution if you dilate the radius by a multiple of 2 or any multiple greater than 1. Okay. The second inequality is just a definition of a little h of r. It's just a triangle there, right? So if you so that's just so what do we do in next is to try to estimate capital H of 2r plus little h of 2r. We want to bound this sum by the L2 average of the solution on a scale 1, on a ball of radius 1. That's what we do here. All right. So so you see in this argument, very little is used in terms of a solution or equations here. And actually, I can summarize the argument we're going to use in a more general scheme. So this is already contributed to Armstrong and Smart, and in one of my papers, I extend this to a more general form there. So they have a different proof, but this is in a different form. So this is, I think, it was more the most general form we can have here. So I have two non-negative functions, h of r and little of hr, on the interval from 0 to 1. Okay, and assuming these two functions satisfy certain properties. The first inequality just saying that for t between r and 2r, the maximum it's controlled by a constant times h of 2r. So I'm not assuming h of r is increasing, but this property would just be fine. Okay, of course, if it's increasing, it's okay, but most likely the function you're dealing with is not going to be increasing. And so what is they say here is that between r and 2r, you can always bound that by h of 2r. And this is particularly useful when you're dealing with average over a ball. You can just dilate the ball, you pay a price of a multiple, that's all. Okay, the second condition is on h little of t. This saying that for two numbers between r and 2r, h of t minus their difference is also controlled by h of 2r up to a constant. Okay. And the third condition is related to what we just mentioned a few slides ago. When you go from theta r to r, you expect this function to decay, well, to increase So here I multiply by 1/2, and then you generate a error term, and that will just be omega of epsilon over r, and plus that sum of two terms. So what we want here is that this omega to be Dini continuous. That when you integrate omega divided by t, I want this to be integrable near 0. And if you have this all the conditions, then you have a maximum of HR plus little h of r for r between epsilon and 1 is controlled by the sum of the values at 1. So this general scheme is tailor-made for what we're trying to prove. But once you have this done, and then we were able to carry the scheme in a different settings. All right, so let me just say, how do we carry this out for the interior estimate? As we said, we need to approximate the solution u sub epsilon by some good functions. The good function will be called W, and W here will be a solution of an elliptic equation with constant coefficients. In this particular case, is exactly the homogenized equation for L epsilon. So I expect this to, so when you measure U epsilon minus W, take the L2 average, I want this to be small. So this is kind of a convergence rate. And this just tells you that in a general scheme, I want the rate to be at least Dini. So any power of t would work. And you can always do rescaling in a setting. So it suffices to prove some convergence rate in a ball of radius 1 there. All right. So with this and with the previous observation, you see that the function I have defined to be h satisfies this inequality, and then we can carry out this general scheme here. So what you see here is that the regularity problem is reduced to a convergence rate problem. So once you have convergence rate, this scheme allow you to transform the regularity from the limiting equation to the solution of L epsilon there. Okay. All right. So for convergence rate, there have been a lot of paper written, and sometimes we try to get the sharp rate as sharp as possible. But in this particular case, all I need is a Dini rate. So any power of epsilon would work. So here I take a bounded Lipschitz domain. I look at the equation L epsilon U epsilon equal to 0 with a Dirichlet condition, and we can prove this rate for some alpha greater than 0. If A happen to be symmetric, you can even take alpha to be 1/2. Okay. And so whether the rate is optimal or not is not important for our purpose, because all we need is just kind of Dini rate will be suffice. All right. So how do you prove something like this? You use energy estimate, but also you need to get the correctors involved. So we look at a difference U epsilon minus U0. U0 is the homogenized solution. And then you have to subtract some term which involve the corrector. So it's epsilon times chi of x over epsilon. The eta there is a cutoff, and S epsilon is a smoothing operator. This is a little bit technical, but it's just pretty straightforward. And then you plug this function into the equation for L epsilon. And so we're able to prove something like this. So on the right-hand side, there's a second derivative of U0, but it gets multiplied by epsilon. Then there's a first order term times epsilon. And omega epsilon here is a layer near the boundary of omega. So omega epsilon is just x in omega, whose distance to the boundary is less than epsilon. So it's a boundary layer there. And then you can, and you see that, and so we get this estimate on the bottom there. Okay, so then the idea is that you try to generate some power of epsilon, and also reduce the order of the derivative. Eventually, you don't want to use a second order because the boundary data is only in H1 actually. Okay, so so you can use the interior estimate to bound a second order derivative. Okay. For some p greater than 2, all right, and then you can use a Neumann Meyer type estimate to reduce the LP norm of the gradient on the domain omega by its H1 data on the boundary, and then finally, when you combine, you have this estimate. Well, sigma it's given by 1/2 minus 1 over p, but since p is greater than 2, so we know this power is positive, and so that's enough. Okay, so then the question: how do you manage the H1 norm on the right hand side? So here is another theorem. This is the theorem we wanted in order to carry out that general scheme. Let's say change B1 to B2. You have a solution there. So then we can find a solution of the homogenized equation in B1, so that the L2 norm, L2 average of U epsilon minus W is controlled by epsilon to some power alpha times the L2 norm of U epsilon over B2. So the idea is that we don't have a boundary condition on the boundary of B2, but our approximation is only good in B1. So we don't really need any boundary condition on the ball of B2. Okay, so so how do you do this? Well, first of all, you use quadruply. So the integral on B3 is controlled by a gradient is controlled by L2 norm on B2. That's just quadruply. And then we use some kind of we call a core area formula. There must be, it's a very simple one here. There must be some parameter t between 1 and 3/2. So the integral on the boundary of the ball is controlled by the right-hand side. How do you see this? You just argue by contradiction. Suppose there's no such t. In other words, for any t between 1 and 3/2, you have a reverse inequality. And then you just integrate t from 1 to 1/3, which generate a contradiction to the quadruply. That's all. Okay. So in other words, when you have a volume integral controlled by the right-hand side, some surface integral must also be controlled by the right-hand side, because the volume integral is the integral of a surface integral. That's what I refer to as a core area formula. It's just you might also call it polar coordinates. Okay, so and that's all we need, because now you just take the W to be the solution in BT, whose boundary data agree with U epsilon on the boundary of BT. And so you will use the previous estimate with H1 norm on the boundary of BT, but H1 norm on the boundary of BT is controlled by the L2 norm of U on B2. And that finished the proof. Okay. Any questions, please? All right, so next I want to show you that this scheme also works really well for boundary estimates without much additional difficulty. Okay, the compactness, there was a hard time getting the Dirichlet and take a lot of many years to get Neumann, is because we did not know how to estimate boundary correctors. But this argument here do not involve correctors. You see, when we try to measure the Lipschitz, we only measure the distance between the solution and the linear functions. We do not have the correctors involved. Okay, so as a consequence, we can still do the regular, boundary estimate. So let's just localize the boundary problem. Let's say to a piece of graph. That's assuming the graph. We'll have to assume the boundary is C1 alpha here. So the psi is a C1 alpha function or C1 sigma function. And so D2 is the intersection of roughly it's the intersection of the domain with a ball of radius 2, and delta 2 is the intersection of the domain with the boundary of it's the intersection of ball B2 with the boundary of omega. So delta 2 is the piece on the boundary. That's the setup here. So here we need to redefine the function h of r or h of t here. The first term is still be the same. It still measure the difference between the solution and the linear function, linear approximation. And you try to take the best linear approximation here. So you take an infill over all E in RD, all Q in R. Okay, and then the capital F is the right-hand side. Previously, we are assuming capital F is 0, so that term is there. So now if you have a general right-hand side, and you want to get LP norm, LP average involved, P has to be greater than the dimension there. And then we might have a boundary condition. So little f is the boundary condition. So here we need to take the look at the difference between f, a linear function, but measure on the boundary. So the gradient of TAN, that's a tangential derivative, L infinity norm. And we also take this C1 alpha or C1 sigma norm. So it's the tangential derivative of C0 sigma norm, properly rescaled. So you have to multiply T sigma there. So that's the setup. You define this function H, and you try to carry out the general scheme and try to verify this condition, this function H of T satisfy the conditions in that general scheme. There are 3 conditions there. Okay. All right. For the Neumann problem, it can be done similarly. The first term is the same. The second term is also the same. The last 2 terms, it's a little different. G is the Neumann data for L epsilon. And D nu is the co-normal derivative of the homogenized equation. So it's a little tricky here, so you don't because the Neumann problem depends on the operator. When you homogenize the equation, the operator gets homogenized, so the corresponding boundary condition it just have to be the variational form of the conormal there. So that's why it's denoted by d nu 0. So you take the difference there, but the idea, the underlying idea is the same. It's you try to approximate, you try to measure the regularity by measure the distance between the solution and the linear functions or affine functions there. That's the setup there. Okay. All right. So let me also mention. Oh, there's okay. So this slide there's a Calderón-Zygmund Estimates. It's also called W1P estimate. So now you have an equation. The right hand side divergence of f, and let's assume u epsilon equal to 0 on the boundary. If you multiply both sides of the equation by u epsilon, you integrate by parts, you have an energy estimate. So the L2 norm of the gradient is bounded by a constant times L2 norm of f. F is the right hand side there. So the question here is can you have LP estimate for the gradient? So that's actually is the Calderón-Zygmund estimates. And so again, so we do and provided the coefficient matrix is elliptic, periodic, and because we're also down to the small scale, so we need this to be VMO. And that can be generalized whenever you have a small estimate for local coefficients, then you can extend that. Because the large scale estimate does not depend on the regularity there. Okay, so the other thing I want to mention here is that so far we have talking about periodic coefficients. And with this new approach, we can actually go beyond periodic. So in particular, we can talk about so-called almost periodic functions. So what is the almost periodic function? Well, you start with trigonometric polynomials. So trigonometric polynomials is just a finite linear combination of exponential functions. Okay, so the lambda there is just a vector. It doesn't have to be an integer point. And AL can be any complex number. So in particular here, you have a sine 2 pi x plus cosine square root of pi x. You see the first term, sine 2 pi x, is a periodic function with period 1. And the second term, cosine square root of 2 pi x, that's particularly cook up to have a period square root of 2. Because square root of 2 is irrational, you add these two functions, it's not going to be a periodic. But nevertheless, it's a almost periodic functions because it's a trigonometric polynomial. Well, the definition of almost periodic functions, there are several definitions, several classes. The smallest one is called uniformly almost periodic, or almost periodic in the sense of both. So these are functions which are uniform limits of sequences of trig polynomials. In other words, if you have a continuous function which can be approximated by trig polynomials uniformly over the whole space, then that function is almost periodic. Okay, so almost periodic is oscillating just like a periodic function, but they don't have to have a period. This is a graph of that function I mentioned there. Okay, so and for almost periodic functions, there's also a theory which is known since 70s, you can homogenize the elliptic equation or parabolic equation there. And the homogenized equation is a system, is an equation with constant coefficients. Okay, so this is the qualitative version here. Okay, so more recent research, last 10 years, last 15 years, is more on the quantitative side. So we know convergence, but can we prove some convergence rate, and can we prove regularity estimate independent of the parameter epsilon, just like in the periodic case? So lots of work has been done there in this direction. The problem when you go beyond periodic coefficients is that you do not have a corrector given to you on the because when in the periodic case, the correctors was obtained by solving a elliptic equation on a cell on a torus, let's say, and that cell or a torus is just the period of the coefficient there. But now you don't have a periodic function, you don't have a cell, and so there the corrector, the existence of the corrector is not even clear. And so the approach here is through introducing something called approximate correctors. The idea is also straightforward. It's like you want to solve an equation in the whole space, but this quadratic form is not coercive because the domain is unbounded. So what you do is that you're introducing a zero order term so that the bilinear form is coercive on H1. So you can apply the Lach-Milgram theorem. So you have a t there, t goes to infinity. So that equation can be solved for each t. And the hope is that as t goes to infinity, there's some limit, which is supposed to be the corrector. And hopefully you can get some uniform estimate with respect to t. And so that's been the approach for general non-periodic setting, including the random case. Okay, so now we need to quantify the almost periodicity, and this is one way to do it. So you look at the translation of the coefficient matrix A. So you have A dot plus Y, and then A dot plus Z. And here, for any Y, you look for the difference between A dot Y and A dot Z. Well, Z is less than R. You see, when A is periodic, for any Y, you can always take the fractional part of Y. Then the difference would be 0. The fractional part of Y will be between 0 and 1. That's assuming it's period 1 there. It turns out in an almost periodic case that this function as a function of R goes to 0 as R goes to infinity. So you don't get a period, but you get this kind of translation decay type property. And so that's how we quantify this almost periodicity. It's kind of measuring the difference between your function and the periodic function. Let me just finish this quickly. So this is a theorem I did with Scott Armstrong. So we are assuming the coefficient matrix is elliptic and uniformly almost periodic, and also Hilbert continuous. Further, we need to, assuming this function rho of R, which is used to quantify the almost periodicity, to have a logarithmic decay for some power n there. And then we can prove this when n is greater than 5/2, then we have a Dirichlet, we have a Lipschitz estimate for Dirichlet problem. And for n, if n is greater than 3, then there's estimate for the Neumann problem. I'm pretty sure this condition on capital N are not optimal, but it looks like some kind of condition on rho of R is required to have a Lipschitz estimate, although I don't have any counter examples. Okay, I think that's all I want to say. Thank you very much.
All right, thank you very much. Let me stop.